In this lesson, you'll be solving for angle measures in right triangles using inverse trig ratios. There are two learning targets listed here. Take a moment and read those learning targets. So in this lesson, the focus is going to be on finding angle measures of right triangles using what's called inverse trig ratios. Before we jump to inverse trig, let's recall the three main trigonometric ratios: sine, cosine, and tangent. Remember, trig ratios are the ratios of two of the lengths of a right triangle in relation to one of its acute angles. In the diagram shown of the right triangle, there is an acute angle that's marked as x. In relation to that angle marked as x, there is a side directly across from it, which we call the opposite side. The hypotenuse is always the longest side in any right triangle, right across from the right angle, and the adjacent side is the third side, which will be touching the acute angle that we're referring to. SOHCAHTOA is the memory device that helps us remember sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. The question here is, can trig ratios help to solve for missing angle measures? Now, up to this point, we have used trig to help us find missing side lengths in a right triangle. Now we want to investigate, can trig also help us solve for missing angle measures? So here's an example. Triangle LMN is a right triangle, as you see, and there is an acute angle L that is marked as our unknown. We want to find the measure of angle L. We know it's less than 90 degrees, but without a protractor, without this being drawn to scale, we have to have some other way of determining this. So what we do is we think about the two side lengths that are given. We have the sides marked as 12 and 5. And we think about our SOHCAHTOA, and we realize we know nothing about the hypotenuse, so we're not going to use sine or cosine. Instead, we'll use tangent. And we write that the tangent of L is equal to 12 over 5. And now we introduce a new notation called inverse tangent, where we're trying to solve for that angle measure, and we're going to take the inverse tangent of both sides. And the notation you're going to use looks like this. You'll notice on your calculator, under the function area or trig area, you will see a button that looks like this. It's in the function area of this Desmos calculator. And I want to find inverse tangent, and then a set of parentheses pops up, and I type in 12 over 5, and the answer of 67 point, and then a lot of decimals show up after that. We typically round to the nearest tenth. So the measure of angle L is 67.4 degrees. And if I wanted to find the measure of angle N, I could remember that the two acute angles in a right triangle are complementary, so I could just subtract 90 minus 67.4, and the measure of angle N would be 22.6 degrees approximately. Let's try another example. The directions say to label all three angles of a triangle. It doesn't say this is a right triangle, but the three side lengths are given as 6, 8, and 10. So the first thing I need to know before I apply my trig ratios is this a right triangle? I can think about my Pythagorean triples, or I can use the Pythagorean theorem. If a squared plus b squared equals c squared, then according to the converse of the Pythagorean theorem, this would be a right triangle. So let's plug in our values for a, b, and c, where c is always the longest side length. And let's square these numbers, 36 plus 64, and check. What is the sum of 36 and 64? It's 100. So because this is a true statement, I know that x is indeed 90 degrees, and this is in fact a right triangle. That's helpful because now I can use my trig ratios to solve for the two acute angle measures. Let's start by solving for angle y. And in relation to angle y, if we use sine, we could do opposite over hypotenuse. So our trig equation could be sine of y equals 8, which is the opposite, over 10, the hypotenuse. And here's the place in the equation where we take the inverse sine of both sides. So y is equal to inverse sine of 8/10. And I find that function button on my calculator, and I get that y is approximately equal to 53.1 degrees. And I check it on my diagram, make sure that makes sense. Now to solve for z, I could subtract 53.1 from 90, but if I made a mistake solving for y, then my mistake carries into z. So what I'll do instead is to look at angle z, I'll think about a trig ratio that could help me solve for it. And I'll think about cosine, the adjacent over the hypotenuse, and I'll write a new trig equation. Cosine of z equals 8/10. I'll take the inverse cosine of both sides. I'll type this into a calculator, and I'll get my answer that z is approximately equal to 36.9 degrees. And then I'll just double check, and this isn't always going to be perfect because we've done some rounding here, but the sum of these two acute angles should be either 90 degrees exactly or very close to, and it is. So that gives me confidence in my work. All right, now we'll look at another example. A right triangle, and some of the measures are given. Find the remaining angle measures and the side length of the triangle. So I'm going to need to find the angle measures, which are x and y in degrees, and side z, which is going to be in units. Let's start by solving for x. And in relation to that acute angle, I have the adjacent side length is given and the hypotenuse. So which trig ratio deals with the adjacent and the hypotenuse? Cosine, very good. And now you can write your equation. Write your first trig equation to help you solve for x, okay? And that's cosine of x is equal to 15 over 17. Now to solve for x, remember we want to take the inverse cosine of both sides, and then we want to type that into our calculator. Well, let's see what you end up with and round it to the nearest tenth. Did you get 28.1 degrees approximately for x? Good. All right, now let's determine the remaining side, z. Let's hold off on y for a second, and let's jump over to our Pythagorean theorem. And let's substitute in our values for a is 15, z is what we're going to use for b, and the c is 17. And let's solve for z by first squaring the numbers and then subtracting 225 from both sides, and now taking the square root. And so I find out that z is 8 units. So this is an 8, 15, 17 Pythagorean triple. And now to solve for the remaining angle measure, let's use the fact that x and y are complementary angles, and let's subtract 90 minus 28.1 to get 61.9 degrees as the measure of angle y.